Okay, we are going to look at an example of a first order linear differential equation. So first off, what does that mean? Any differential equation, right, which means has a derivative somewhere in there, right, y prime. But if we have it in this form, where we have some function of x, a of x, right, and uh, y prime, so dy dx, and then b of x and c of x are also functions of x, where we have y prime, y, and then on the right hand side just all functions of x. Sometimes you need to manipulate the equation first to get it into this form. This one, however, we could see it's directly of this form, right? The only maybe confusing part is this example has y before cotangent x, which is a function of x, but that's simply because if we didn't use parentheses, right, then that is open to interpretation of, do we mean cotangent of x multiplied by y, like this, or do we mean cotangent of xy, right? So to avoid confusion, we often just write the variables separate if that is what is intended. All right, if any manipulation occurs, right, if we have a factor, if we have a coefficient in front of y prime, you divide everything by the a of x. Okay, similar to a quadratic perhaps, where you divide your a of x. Then, if you do that, we just call that resulting coefficient of y, the b of x over a of x here, we call it p of x. And then the right-hand side c of x over a of x, we call it q of x. All right. So let's dig in. Step one, we have to define the integrating factor. Okay, the integrating factor is defined by rho of x. We take e to the power integral px dx. Okay, I'll often do this to the side because it is a side step of finding what rho of x is. All right, so step one, we need rho of x. It is e to the integral. Remember, p of x is cotangent. Q of x is cosine. Okay, so e to the p of x, e to the integral cotangent x dx. And to integrate cotangent, there are formulas, but this one, use substitution, we could actually do that just fine, right? Because we have e to the integral cotangent is cosine x over sine x dx, and using u substitution, didn't mean to make this Christmas colors, but that's okay. If we call u sine x, then du is cosine x dx, and therefore we have integral e to the du over u, which is ln, right? Du over u is ln, e to the ln u, which I'm going to go ahead and write in here, sine x. Okay, often when we do these, it will all work out where we know that that would be positive. So why do we know that right now? Well, remember, there's a domain restriction. You cannot take natural log of a negative, right? So that's why that has to be positive. But we will see sine x is going to be positive anyways. I'll leave it for now, and we'll address that later. All right, so ELN cancel, and we just get sine x. Okay, that is your integrating factor. That's rho. So step 2, multiply everything by rho. So therefore we would have, okay, I'm just going to write it like this to show we are in fact doing that. And I know you can't really multiply across this equal. You get the point, right? We're multiplying everything by rho. So therefore we would have sine x, y prime, sine x. I'm going to change y prime now to dy dx. Actually, let's keep that black. Plus, so we have that y again. I'm going to write it here. So we're multiplying by sine x, and then cotangent, right, that's cosine over sine. And then on the right-hand side, we have our cosine times sine x as well. All right, so in red, I put the integrated factor that we in fact distributed everything and multiplied. Anything in color were changes. Okay, so we could see here those cancel. So we have y cosine. Not that it even matters, because by default, step 3, and we could always verify, and there's a proof of this, but step 3 by default grants us the fact that we're going to have the derivative of rho times y of x. So rho was sine of x, and then times y. Only to stick with this notation on the right over there, I will go ahead and write it. I would really prefer to write the y in front like we have been, but that's okay. So let's check that. Like, does this whole left-hand side really become that? I mean, it's kind of crazy. So we have product rule, right? F times G. And we have implicit differentiation. So F prime G, so derivative of F is cosine times Y. Well, that's exactly this, right? This is F prime times G plus FG prime plus sine X, there's F. Derivative of Y is 1, but implicit differentiation, dy dx. There it is, product rule, it checked out. Okay, you could always do a quick check just to make sure your steps were correct so far. Okay, right hand side we have sine x, cosine x. So we're going to integrate. I didn't really write this next step, but we need to move dx to the right hand side. So I'm going to move this dx over here, and then what we do is integrate. All right. Now, why does that work? Because remember, fundamental theorem of calculus, the integral of a derivative cancel out, their inverses. We do have to worry about this constant and whatnot, but that's taken care of on the right. All right. So what am I saying? I'm saying this integral of this derivative cancels. Okay, so that integral derivative cancel, and we get, just, I'm going to rewrite it now, y times sine x. Okay, and on the right-hand side, we have integral sine x cosine x dx. All right, you could integrate this in two different ways I'm seeing, because we could get a double angle formula here and integrate. Probably, and we could get a different answer. That's right, you've seen in calculus that could happen, depending on your substitution. I'm going to go ahead, though, and just call u, just like we did over here, right? I'm going to use that same substitution. If u is sine of x, du is cosine x dx. So therefore, my integral is just u du. Okay, and that is u squared over 2 plus c. And of course, we need to substitute our u back in, which we knew was sine x. Okay. All right, so step 4 is done. We integrated. We have to solve for y. We need to divide everything by sine. So let's do that. Okay, if I have sine squared and I divide by a sine, one of them would cancel. So our result, our function y, is equivalent to, I'll just write that as 1/2 sine x. And dividing by sine is cosecant, right? So it's up to you, but we'll go and do c times cosecant x. I guess it looks a little cleaner. Okay, that absolute value, so we do have to think about that. So do we need it? When we multiplied by that integrating factor, sine x, so here I could see we're squaring it, so that is irrelevant, right? So that sine x is going to be positive. We could keep that. And now really the only other one we have to think about is this here. But since c is a constant, it doesn't matter, right? It could be positive, it could be negative. If I said a negative c or a positive c, that really doesn't matter. Many times as well, there will be fine print saying assume the variable is positive. I don't think it's going to matter in this case. Okay, so our solution is here.